Dear students, do you want to get into the fascinating world of physics? Please see this video and also subscribe to this channel.
Dear students, in this video we are going to study about lateral magnification in thin lenses, power of a lens, focal length of lenses in contact, and also about silver lenses. Dear students, in this video we are going to study about the lateral magnification in thin lens. For this, let us consider an object OO dash of height h1 placed on the principal axis, which is a height perpendicular to the principal axis. The inverted real image II dash is formed, which has a height h2, which is as shown in this diagram. So this is the thin lens, and the object is kept at this point OO dash, having a height h, and the rays are like this, and therefore the image will be formed at this point II dash, and this height is about h dash. The image distance is u, and the image distance is v here, the object distance is u, that's given here. So this is how the object is magnified, and we can see as an image right at this point. The lateral or transverse magnification m, that is defined as the ratio of the height of the image to the height of the object. So the expression can be written as m is equal to II dash by OO dash. And from the two similar triangles POO dash and PII dash, we can write II dash by OO dash equal to PI by PO. So by applying the sign convention, we can have minus h dash by h is equal to v by minus u. Substituting this equation in 6.65 for magnification, we have m is equal to minus h dash by h, or that's equal to v by minus u. And after rearranging, we have this expression m equal to h dash by h, that's equal to v by u. So this is given by the ratio of image distance to the object distance. That will give you the magnification of a thin lens. This magnification is negative for real image and positive for virtual image. In the case of a concave lens, the magnification is always positive and less than 1. So we can also have the other forms of equations for magnification by combining the lens equation as m equal to h dash by h, and that's equal to f by f plus u, or m is equal to h dash by h, or we can have f minus v by f. Then we will study about the power of a lens. What is power of a lens? That is the measure of its deviating ability on an incident light. That will give you the power of a lens. So when a ray is incident on a lens, then the degree with which the lens deviates the ray is determined by the power of the lens. And the power of a lens is inversely proportional to the focal length. That means the greater the power of a lens, the smaller will be the focal length. So for lenses having a small focal length, its power will be very much greater. So that is what given in this diagram 6.36. So here this will explain the power of the lens. And for a short focal length, the power of the lens will be greater. So here in that case, the second diagram has, that is the second lens will have greater deviating ability and its focal length will be less, and vice versa. So that is what explained here. And the power of a lens is a measure of the degree of convergence or divergence the lens produces on the light falling on it. The power of a lens P is the reciprocal of its focal length in meters. So that is P will be equal to 1 by f. What is the unit of power? It is diopter, which is denoted by letter D. And 1 diopter will be equal to 1 meter power minus 1. Its power will be positive for a converging lens and negative for a diverging lens. From the lensmaker's formula, the equation 6.62 to 6.68 can be written for power as P equal to 1 by f. That will be equal to n minus 1 into 1 by r1 minus 1 by r. The outcome of this equation for power is that for a given geometry of the lens, larger the value of refractive index, greater is the power of the lens, and vice versa. And for lenses with small radii of curvature, which will be bulky, the power is large, and for lenses with large radii of curvature, it will be skinny in nature, the power is small. Next, we are going to study about the focal length of lenses which are in contact. For this, let us consider two lenses 1 and 2 of focal lengths f1 and f2 placed coaxially in contact with each other so that they have a common principal axis. And for a point object placed at O beyond the focus of the lens 1 on the principal axis, an image will be formed by it at I dash. And this image I dash will act as an object for the second lens, and the final image is formed I as shown in this diagram 6.37. As these two lenses are thin, the measurements are done with respect to the common optic center P between the two lenses. So this is the first lens and this is the second lens, and this will be acting as the common optic center. The object is kept at this point O. You will get actually the image I you should get, but as these you will have a combination of two lenses, the image will be obtained at this point I dash, and U is the object distance and V is the image distance, and V dash is the image distance. So for the first lens, the object distance PO is U and the image distance PI dash is V dash, and for the second lens, the object distance PI dash is given by V dash and the image distance PI is given by V. So the lens equation for the first lens is given by this expression 1 by V dash minus 1 by U equal to 1 by F1, and the lens equation for the second lens is given by this expression 1 by V minus 1 by V dash equal to 1 by F2. And adding these two equations, we will get 1 by V minus 1 by U equal to 1 by F1 plus 1 by F2. The combination will act as a single lens of focal length F, so that for an object at a position O, it forms the image at I. So the equation can be written as 1 by V minus 1 by U equal to 1 by F. Comparing the equations, we get this expression 1 by F equal to 1 by F1 plus 1 by F2. So this equation can be extended for any number of lenses which are kept in contact, and therefore we get this expression 1 by F equal to 1 by F1 plus 1 by F2 plus 1 by F3 and so on. This above equation can be written in terms of power of the lenses as P equal to P1 plus P2 plus P3 plus P4, as P1 is given by 1 by F1, P2 as 1 by F2, P3 as 1 by F3 like this. So P is the net power of the lenses in contact, and we should note that the sum is an algebraic sum, that is the sum of the powers of the lenses. It will be an algebraic sum. The powers of individual lenses may be positive for convex lenses and negative for concave lenses. The combination of lenses helps to obtain converging or diverging lenses of desired magnification. So a combination of lenses enhances the sharpness of the image. As the image formed by the first lens becomes the object for the second lens and so on, the total magnification M of the combination is a product of magnification of individual lenses. Therefore, the expression for the magnification of the combination of lenses is given by M is equal to M1 into M2 into M3 and so on. That is M1, M2, M3 are the magnification of individual lenses. Now let us study what is a silver lens. If one of the surfaces of a lens is silvered from outside, then such a lens is said to be a silver lens. A silver lens is a combination of a lens and a mirror. Light can enter through the transparent front surface of the lens and get reflected by the silver coated rear surface. So light will travel 2 times through the lens, which is as shown in this diagram. The power of a silver lens is given by this expression P equal to P1 plus P1 plus Pm. So that can be written as P equal to 2P1 plus Pm. P1 is the power of the lens and Pm is the power of the mirror. We know that the power of the lens is the reciprocal of its focal length, that is P equal to 1 by F. that is shown here. The power of a mirror is negative for the reciprocal of its focal length. So that means P equal to minus 1 by f. So this is because a concave mirror which has negative focal length is a converging mirror with positive power. The silver lens is basically a modified mirror. Therefore, the power P can be written as 1 by minus f, or P1 equal to 1 by f1, Pm equal to 1 by minus f. So the equation 6.78 will be written as 1 by minus f equal to 2 by f1 plus 1 by minus fm. So the sign conventions are to be followed carefully. Suppose the object distance u and the image distance v are to be found, we can very well use the mirror equation. So the silver lens is a modified mirror. Therefore, the expression can be written as 1 by v plus 1 by u equal to 1 by f.
All right, let's jump right into it. Welcome to this explainer, where we're going to uncover the optical physics behind how we, well, bend light to our will. Light it's truly mystical, right? Yet its behavior in ray optics is incredibly precise. Today, we're breaking down the everyday magic sitting on your face right now. Yeah, your glasses, as well as the tech in cameras and microscopes. We're taking the abstract physics of ray optics and translating it into the practical reality of how we manipulate light to actually see the world more clearly.
So how do we bend light to capture the perfect image? Let's look past the illusion of the camera. To really understand how simple pieces of curved glass can be measured, stacked, and modified to create these powerful optical tools, we have to start at the very foundation: thin lenses. At its core, a lens is just transparent material sandwiched between two curved surfaces, or maybe one flat and one curved surface. But, how do we actually measure what that piece of glass is doing to the light? How do we quantify its ability to change what we see?
Well, our very first building block here is lateral magnification, which you might also hear called transverse magnification. It's a beautifully simple concept. It's literally just a ratio comparing how tall our generated image is to the actual real-world object. Think about it. If you have an object that's 1 centimeter tall and your lens projects an image that's 3 centimeters tall, your magnification is simply 3. We measure this perpendicular to the principal axis of the lens, but in physics, this simple little ratio tells a much deeper story about where that image actually is and what it looks like.
We can actually use math as a physical metaphor here. See, magnification isn't just about heights, it's also exactly equal to the ratio of the image distance, which we call v, over the object distance, which we call u. Now, because of the strict rules of how we map out light rays, the signs in this equation act like a cheat sheet for what your eyes are going to see. If your formula spits out a negative number, your image is real, but it's flipped upside down. On the flip side, a positive magnification means you're looking at a virtual image that's standing perfectly upright. The math perfectly dictates the physical reality. It's pretty amazing. But here's the thing. To magnify anything, a lens needs muscle. It needs the physical ability to deviate a ray of light that falls on it. And this brings us to a really fundamental concept in optical engineering, which is optical power. When a ray of light hits a lens, the degree to which that lens bends or deviates the ray is determined entirely by this power. Simply put, the greater the power, the sharper the bend. And that power is deeply tied to the physical geometry of the lens itself. Thick, bulky lenses with small radii of curvature, they aggressively deviate light. Because they bend light so sharply, those light rays converge super quickly, resulting in a short focal length and, as a result, a very high optical power. On the other hand, skinny lenses with large radii of curvature barely bend the light at all. It takes a really long distance for those rays to finally meet up, which means a long focal length and very low power.
So the absolutely crucial point here is that this power is simply the reciprocal of the focal length in meters. We calculate it with a beautifully simple equation. P equals 1 over f. So the next time you look at your glasses prescription and you see a diopter rating, you are actually looking at a measurement of optical muscle. 1 diopter is equal to 1 inverse meter. It's also really worth noting that power is positive for a converging lens and negative for a diverging lens. So by just glancing at that diopter rating, you instantly know both the direction the light is bending and exactly how aggressively it's being bent.
Now you might be wondering, if one single lens has all this magnifying power, and we can mathematically design it to have literally any diopter we want, why do we need anything more to take a good picture? Why don't cameras just have one single, solitary piece of glass on the front? Well, as it turns out, relying on a single lens has some major limitations when you're trying to capture a crisp, detailed, and highly magnified image of the real world.
And the answer to that problem lies in combination lenses. What we're looking at here is a system of combination lenses. Combining multiple thin lenses coaxially, right in contact with each other, vastly enhances the overall sharpness and magnification of the image. Just like the optics inside your smartphone or a high-end professional camera, these systems use the image formed by the first lens as the object for the second lens, and so on. This stacking technique helps optical engineers get the exact converging or diverging behavior they want, all while removing the blurriness you'd inevitably get from just using a single thick piece of glass.
And honestly, there is a beautiful simplicity to the math of stacking lenses. While combining focal lengths involves adding all these messy fractions, just look at power. When you stack lenses, their optical powers simply add straight up in a basic algebraic sum. A 2-diopter lens plus a 3-diopter lens just gives you a 5-diopter system. Boom! And even better, their individual magnifications multiply together. So if the first lens magnifies the image 2 times and the second lens magnifies it 3 times, your total magnification is a massive 6 times. It makes designing complex optical instruments remarkably straightforward. Okay, now let's see how this all builds into what I like to call an incredible optical plot twist: the silvered lens. Up until now, we've only talked about light passing purely through transparent material. But what happens if you take one of the surfaces of a thin lens and silver it from the outside? Well, you create a brilliant hybrid. You're combining the refractive properties of a lens with the reflective properties of a mirror.
When you paint the back of a lens with silver, a photon's journey changes completely. Just think about the path of the light for a second. First, the light enters and refracts through the transparent front surface of the lens. But wait, it can't escape out the back. Instead, it hits that silver-coated rear surface, bounces off, and travels back, refracting a second time out through the front. So the light actually travels 2 full times through the lens itself, with a mirror bounce perfectly sandwiched right in the middle.
Because it relies on bouncing light back to exactly where it came from, this combination of a lens and a mirror effectively becomes a powerful mirror itself. In fact, when we're dealing with silvered lenses, we can actually just use the standard mirror equation to find our object and image distances. It behaves just like a mirror, but one that has had its optical power completely supercharged by the lens material sitting right in front of it.
That 3-step photon journey we just discussed perfectly explains the formula we use to calculate the power of a silvered lens. The total power is the power of the lens plus the power of the mirror plus the power of the lens again. Or, to put it simply, double the lens's power plus the mirror's power. Because the light refracts through the glass twice, its deviating ability is literally doubled before the mirror's power is even added to the equation. And here is the truly wild part about all of this. Even if the lens itself has a negative focal length, silvering the back can result in a positive overall power, creating a completely converging system. How cool is that?
So, the complex tech in your pocket, or sitting on a laboratory workbench, isn't magic at all. It's just a clever, mathematically precise combination of basic, lateral magnification, power addition, and reflection. By altering radii of curvature, stacking lenses to multiply magnification, or even silvering the glass to double its power, we can totally master the rays of light. So the next time you marvel at a stunning zoomed-in photograph, ask yourself, what other hidden optical hybrids do you think are manipulating the way we view the universe? Keep questioning, keep observing, and thanks so much for joining me on this explainer.